So hi everyone, and welcome to this session. This session is going to focus on emerging research at BTR4. We have about 6 presentations lined up today with speakers from various fields. My first presentation here is Built for Active Travel, investigating the contextual effects of the built environment on transportation mode choice. This authors are Gamal Eldeeb, Moataz Mohamed, and Antonio Paez. So we can go ahead to the first presentation now.
Hello everyone, my name is Gamal Eldeeb, and today's presentation will be about investigating the contextual effects of the built environment on transportation mode choice. This research was part of my PhD research at McMaster University, Canada. So this presentation is outlined into 5 main sections: research motivation, research objectives, data and methods, results, and finally conclusions. So speaking of the motivation, we all know that our urban transportation systems suffer from a lot of problems like congestion, delays, elevated greenhouse gas emissions, and so on. And the primary cause of all these problems is the excessive use of private vehicles. And as transportation planners, our focus should be about luring people out of their cars into more sustainable transportation modes. So the aim of our research is twofold. First, investigating the influence of built environment and socioeconomic characteristics on travel behavior. And second, examining to what extent city geography moderates the impact of built environment attributes on travel behavior. So the main question we were trying to answer is, does the built environment influence mode choice uniformly in a region or not? So we utilized a primary dataset collected through an online survey, which is the Hamilton Street Railway Public Engagement Survey. This survey was structured into 4 main independent sections: socioeconomic characteristics and travel behavior, service quality aspects about HSR operation and planning, also stated preference experiments, and finally attitudinal and behavioral orientation towards public transit and also towards private vehicles. We also utilized other data sets like sidewalks, bike lanes, land use layers, roads network, and those data sets were collected from the City of Hamilton Open Data Catalog. We also utilized discrete choice models along with the spatial expansion methods to investigate the spatial impact of the built environment attributes on mode choice behavior. We used a nested logit model to account for the correlation between alternatives, and actually we found some correlation between non-motorized modes in our case study. And our built environment attributes were spatially expanded using a quadratic polynomial trend surface to obtain spatially varying coefficients. So speaking of the variables we used in the model, so first, our dependent variable is the primary mode choice. So we accounted for walking, biking, public transit, car driver, and car passenger. So in the survey, respondents were asked, what is your primary travel mode choice during the week? Okay. So our independent variables include socioeconomic characteristics, journey time, built environment attributes, and geographic variations. For the socioeconomic characteristics, we included like many things like age, employment status, gender, number of vehicles per household, and the ability to drive. For the built environment attributes, we accounted for 3 attributes: land use entropy, sidewalks density, and bike lanes density. And for the geographic variations of the respondents, so the place of residence of each respondent was geocoded based on the voluntarily reported digits postal codes in the survey. And as you can see here, this figure shows the distribution of the considered built environment attributes over the city of Hamilton. So after many trials of estimating, testing, calibrating our model, finally we have the results. So the results will be explored in three stages. First, our findings regarding socioeconomic characteristics, then regarding built environment attributes, and finally we will present a simulation exercise for improving built environment attributes and how this will influence travel behavior in the city of Hamilton. So as we can see here for the socioeconomic demographics, we found that young respondents are more likely to consider transit or car passenger than others. Also, we found that students and part-time employees are less likely to drive compared to others. Also, we found that females are less likely to choose walking or public transit as their main travel modes. And for journey time, we found that respondents with reported trips less than 15 minutes are more likely to walk and less likely to choose car driver or public transit. For built environments, we found that sidewalk density is positively associated with walking and public transit travel modes. Bike lanes has a positive correlation with biking, while a negative correlation with public transit. And land use entropy is negatively associated with the use of the car passenger travel mode. And we also found that the components of the quadratic polynomial trend surface are significant, which means that the efficaciousness of those built environment attributes is not uniform across the city of Hamilton. So now we will talk about the simulation exercise. So we decided to map the probabilities of Hamiltonians' transportation mode choices to better understand the variations of travel behavior over geography, and also to contrast the variations in travel behavior due to improvements in built environment attributes. So we adapted 8 different Hamiltonian profiles or personas to map the existing mode choice probabilities and also the expected mode choice probabilities due to improvements. So the personas represent the majority of the workforce in Hamilton. We have full-time and part-time employees, male and female. Also, it represents like students with no vehicle as a representative for disadvantaged transportation groups. And also we included retirees to represent the most vulnerable age group. So this figure here shows the probabilities of choosing travel modes across the city with respect to each profile. So we can see that for walking, the probability is higher near the CBD area and like near places where the built environment attributes are relatively high, especially for profiles 5 and 6, which are student. Also, we can see that for the biking, the probability is low across the city. However, it's relatively higher, like in the west part of the city, especially for profiles 3 and 5, like male part-time employees and male students. Also, by looking at the public transit, we can see that the probability is relatively low across the city, except for profiles 5 and 6, also like students. For the car driver travel mode, we can see that the probability is substantially high across the city. Also, it's worth noting that there is there are systematic differences between males and females, where like female profiles have a higher tendency to choose a car. By looking at the car passenger travel mode, we can see that the probability of choosing this specific mode is relatively low across the city, except for the profiles 7 and 8, which are retirees, and also like near places where the built environment is relatively poor. So after that, we wanted to examine the influence of improving the built environment on mode choice. So we assumed significant improvements to sidewalks density, bike lanes density, and land use entropy. And then we found that the results show that improving the built environment attributes will positively affect walking and biking, active transportation modes, while negatively affecting other modes like car passenger, transit, and car driver. And this figure here on the right shows the average probability of mode choices before and after the improvement. And we can see that the most benefited profiles are profile 5, 6, and 3, which are students and male part-time employees. So finally, we can say that our research has yielded the following conclusions. First, built environment attributes and socioeconomic characteristics play a pivotal role in explaining mode choice behavior. Sidewalks density is positively associated with walking and public transit travel modes. Bike lanes density has a positive correlation with biking, while a negative correlation with public transit. Land use entropy is negatively associated with the use of the car passenger travel modes. Also, improving built environment attributes across the city will positively affect active travel modes while negatively affect the probability of considering other modes, including public transit. And finally, the influence of improving built environment attributes is not homogeneous over the city geography. Before ending this presentation, I'd like to mention that for the interested reader, like a full text can be accessed through the Journal of Transport Geography. Thank you all for your time, and please, if you have any questions, do not hesitate to contact me, and thanks again.
Thank you very much for that presentation. We see that some of the team members from the presentation are available here. So I would like to open the floor for questions. If anyone has a question on the study and would like to know anything from the team, please go ahead, unmute yourself, and you may ask your question, or you can write it on the chat and we can go over each question. So I have one question for the team. Were weather conditions, taken as a matter of consideration for understanding active mode use and the impacts of improving built environment on usage? Was that a consideration for the study?
Okay, perfect. So just to give you a bit of context in the city of Hamilton, in let's say province of Ontario, we have a swing around like 70 degree, like negative 35, let's say negative 30 to positive 30 between the difference between summer and winter in Hamilton. So when we collected the data, we explicitly asked the respondent to identify their primary mode of transportation associated with each season. So what's their primary mode of transportation in the summer, and if this will change considering the weather impact. So when we get into this analysis, we took the fall season as our base model and assume that this will cover summer and autumn as well. However, winter will remain as anomaly for several reasons, not only the cold weather, but also how frequently bike lanes are actually cleaned. If we have black ice condition, like people will tend not to walk or bike to work. It's pretty dangerous. And also, if the snow blowers is actually, if the bike lane on the side of the road and the snow blower cannot access the bike lane, so all the snow will be blown into the bike lane, so the bike lane will not be accessible anymore. So this is why we excluded winter from our analysis. But from bike sharing data that I recently seen in the city of Hamilton, like using bikes will almost diminish in the winter.
Understood. Thank you so much for that. Does anybody else have any questions before we move on to the next presentation? Thank you so much, Dr. Mohamed.
Okay, perfect. Thank you.
So the next presentation is application of transfer learning in interpretable machine learning based mode choice model, a case study in San Francisco Bay Area. The authors are Samantha Barua Chowdhury and MD Sami Hasnine. Samantha Barua Chowdhury is our presenter, and I would like to ask Samantha to start by introducing herself and then moving on to the presentation.
All right, thanks, Nikhil, for giving me the floor. I'll share my screen. Okay, so our paper today is the application of transfer learning in interpretable machine learning based mode choice model, a case study of San Francisco Bay Area. I am Samantha from the University of Alberta, and I have my co-author Mohamed Sami Hasnine, who is an assistant professor of the Howard University. So before we dive into our presentation, I would like to give you an outline of the topics we're discussing. First, we'll give you a background and an objective for the motivation behind this paper. And then we'll be explaining some of the machine learning models and the econometric models. And before we dive into our results, we'll give you a brief primer into the techniques that we used. And then we estimated like our results using feature importance and the ALE plots. And finally, we'll show our conclusions regarding our work. So the background of this paper, we aim to investigate the interpretability of the machine learning models and the transferability of the knowledge developed to increase the understanding of the behavioral variables. Normally with the machine learning models, what happens is that only the goodness of it is calculated, which is not enough for developing an advanced comprehension of the models. And although a lot of research has been conducted, with these models, limited research efforts have been devoted to interpretation of these models for enhancing the degree of understanding of the travel mode choice behavior. On the other hand, although econometric models are like the state of art and used for data forecasting, a major limitation of this model is its inability to transfer the knowledge across multiple domains without calibration. So in our paper, we explored the temporal transferability of the machine learning models for two data sets, for AM dataset for 6 to 10 AM, which is used as a training set, and our PM 3 to 6 PM dataset, which is used as a testing set. So our objectives for this paper include the exploration of the interpretability of machine learning mode choices for traffic mode choice behavior. We'll be doing a comparison of the results among different machine learning and econometric models. And then we'll also explore the transferability of the knowledge developed by our machine learning model across the AM and PM datasets. So first, let's dive into our machine learning models. Although we had a lot of options, including like the regressions, the random forest, support vector machines, naive Paez, in the end, we decided to go with the two main techniques, the random forest and the extreme gradient boosting. The reason behind this was that since random forest algorithm operates on a divide and conquer principle, and it easily adapts to the non-linearities found in the data set and are well suited for a larger data set, which is the one that we used for our study. And then on the other hand, the extreme gradient boosting is a regression of trees which works like a sequential ensemble algorithm, and it works very well for data set with a smaller number of trips. So these are the like models that we chose for our research work. And then let's dive into the econometric models. Mainly, we used three models. These are the multinomial logic model, the nested logic model, and the cross-nested logic model. These econometric models are like the discrete choice models where the decision maker can select the modes. In our paper, we have mainly 5 modes, which are the auto drive, walk, bike, public transport, and ride hailing. So let's dive into our like standards for which we'll be discussing the accuracy across models. Here we chose the balanced accuracy, which is calculated with specificity and sensitivity, where specificity includes the ability of a test to correctly identify the absence of a condition or the negative tests, and sensitivity says the ability of a test to correctly identify the presence of a condition. And we chose balanced accuracy in particular because our data set is an imbalanced one. So we wanted to make a fair comparison among the models. So for our data description, we chose the National Household Travel Survey data of the San Francisco Bay Area. Our data set initially consisted of 264,234 trips, but then we had to make sure that we were filtering out the required features. There were no null features in our data set, and each row was complete with a number of information in all fields. So as a result of the filtration done, the total number of trips in our AM dataset was 3,481, and that for the PM dataset was 3,725. So if we go into the feature importance of models, at first, we considered all the modes together, and we compared the feature importance between the two, like the machine learning models, the random forest and extreme gradient boosting. If you look at the figure, we will see that for both the models, the trip cost by driving and the travel distance were the two most important features. And the reason why the cost of driving came up is because the mode driving consists of 72% of the total modes in our data set, which is like the highest percentage. If we look into the other variables, we will see that for random forest, the travel times of modes are much important than the other ones, whereas for XGB, the age and the number of workers per household are seen to gain more importance. We wanted to compare it with our econometric model results, although it's important to realize that it's not always fair to compare the magnitudes of different parameters of logic models with directly from the model. And if we want to do a more accurate comparison, comparing the elasticities of the logic model is a far better option. Keeping this limitation in mind, we compared the econometric and logic machine learning models on the base of their variable importance. And if we look at the differences, we will see that the age of the people and number of households with or without children are seen to gain more importance for our logic models, whereas the travel distance and the cost of the trips have gained more importance for a machine learning model. And thus we can make a comparison between the results gained from our machine learning and the econometric models. If we compare the accuracy of our machine learning models across all modes, we will see that the modes drive and walk have gained the most accuracy. And this is the reason we see where there is a number of trips for a particular mode, the results obtained in random forest in general are far superior compared to the XGB model. On the other hand, if you look at the ride hailing mode, we will see that the extreme gradient boosting actually was able to derive some results, even though this mode has the lowest number of trips in our data set. So from this, we can say that the extreme, although random forest gives us more accuracy, the extreme gradient boosting actually lets us to interpret the results even when the data set provided is of a very small size. And then to further increase the interpretability of our models, we also ran the models for individual modes. Here, for machine learning models, we can see that in general, although the travel cost, travel distance, and travel times were the most important features, depending on the features, on the modes, the features also varied. For example, for drive, we can see that the travel cost and the travel time of drive were the most important features, and the same thing repeats for every other mode. And if we compare the accuracy of our machine learning models for the individual modes, we will see that this accuracy for specific modes were far robust than when calculated for all modes together. This shows us that when models are developed with specific features catered to specific models, we get a far superior accuracy. And then to also derive some other interrelations between the features, we also developed some ALE plots, which is the accumulated local effect plots, that shows the relation among the features within our model, keeping their correlations in mind. So if we see the figure A, we will see that for people who are working part-time, there's a higher propensity to use public transit rather than driving for their commute. So from here, we can give a policy recommendation is that to promote the preference for public transport, incentives can be introduced as a reward for employees who choose to travel through the transits. And if we also look at our figure B, which is the trip destination purpose, here one denotes the trips generated that were for work or for school. And if we see our figure, we see that actually for going to work or school, there was a higher propensity for people to drive. And actually there's a negative correlation with the walk, bike, and the public transit and the other modes. And if you also look at some other features, for example, the household with children from ages 0 to 16 or single parent with no children, we see that in general, people choose to drive for commuting from one place to another compared to any other modes. Then to demonstrate the transferability of the learning across different models, we also ran our models for transfer learning, where we chose the AM dataset as a training and the PM dataset as a training set. And if you look at our result, we will see that similar to like all the modes together, the random forest and extreme gradient boosting in general shows a balanced accuracy of above 80%. From here, we can see that there is actually, for machine learning models, we can successfully transfer the temporal knowledge from one domain to another. And we also repeated the same process for individual modes. And we see that like our previous results for individual modes, the accuracy in general for both the machine learning models were much higher compared to the all modes together. So from here, we can draw our conclusions is that the results generated by the machine learning and econometric models, although they're different in nature and the way they work, they actually are able to complement each other for interpretation of the travel mode choice behavior. We have seen that the random forest demonstrates Robert's performance in comparison to extreme gradient boosting in terms of balance accuracy, whereas extreme gradient boosting are able to handle the smaller data sets more effectively compared to random forest. And then we have also shown that the machine learning models support temporal knowledge transferability, which means that the knowledge of one domain can be applied to another one with a different time frame. And since we have seen that people in general are more inclined to drive due to public transit having more commute time, so from here we can deduce that public transit ridership can be increased by increasing the frequency of trips of the public transit systems, since that can result in lesser commute time for people and ultimately encouraging them to use transit for the commute. we would like to conclude our presentation on that. We highly appreciate any questions or comments on the paper, and you can also reach to us through our emails. Thank you so much.
Thank you for that very interesting presentation, Samantha. I would like to now open the floor to questions. Anybody from the chat or from the window who would like to ask questions? I see that there's one question in the chat, which we'll get to, but anybody else who wants to speak up, please. So I see that there are a few questions here. The first question is from Shuwei Lin. How about neural networks?
I would like to thank Shuei Lin for their question. It's actually a very interesting area to explore about the neural networks. However, within our given time frame and for making a fair comparison among the models, we chose the random forest and extreme gradient boosting, since we thought that they would be able to like handle the complex nature of our data set fairly enough.
The next question is from Thomas Hancock. Did you have any very different results from the econometric models in comparison to the machine learning models, i.e. differences in relative importance of attributes? Samantha?
Yeah, I would encourage my co-author, Sami Hasnine, to take this.
Yeah, Dr. Hancock, yeah, we compared both the machine learning and econometric models. So in the econometric models, we found that the time cost and the distance coefficients a little bit less in magnitude. However, we did not actually calculate the elasticity. So I would say if we would, calculate the elasticity of all the parameters, that we could, 100% confirmly say that they are a little bit different. However, in terms of magnitude, the time cost and distance a little bit less than the other coefficients. What we did actually, we tested the same set of parameters for both machine learning models and econometric models. In terms of sign, they're actually same. The only one thing we need to just confirm is the value of the elasticities. Then we can more accurately capture the difference between them. The other question I saw in the chat, welcome. The other question I saw in the chat that Mr. Lin asked whether why we did not try econometric model to test the temporal transferability. Econometric model requires calibration. So the model that Samantha estimated, she did not do any calibration. So without calibrating that, what we got is really a good result. So ideally, yes, we could use econometric model then, but there is just one extra step that is required, that we need calibration. Then we can definitely do econometric for forecasting. But it's just interesting to see whether the temporal transferability, the machine learning model works fairly well without doing that extra step of calibration. Thank you.
Thank you so much for your questions. Thank you, Dr. Hasnine. Thank you, Samantha. Now we can move on to the next presentation if nobody else has any more questions. The next presentation is Auto Carrier Loading Optimization in Automobile Shipping, a Space State Network Formulation. And the authors are Sajeeb Kirtonia, Yanshuo Sun, and Zhi-Long Chen. Sajeeb is going to be our presenter. Sajeeb, would you like to start by presenting a brief bio about yourself before we move on to the presentation?
Yeah, sure. Thank you, Dr. Nikhil, for giving me the floor. So my name is Sajeeb Kirtonia. I'm doing my PhD in industrial engineering at Florida State University. So this is the first part of my dissertation. So the topic is selection of auto carrier loading policy in automobile distribution. So, okay, let me presentation. Yeah, okay. So the background is automobile shipping problem arises from various contexts, like new cars that distribute to the dealer locations, then shipping automobiles to developing countries, and also people order cars online, want to get the delivery to their home. Also, when people
Hi,
migrate.
Sajeeb.
Yeah.
We're not able to see your presentation. I don't know if it's just me or just want to make sure
Okay. Yeah. Okay.
we're able to see your
Okay.
presentation.
Yeah.
Thanks.
Let's check. Yeah. Yeah, I think we can see. Can you see now?
Yes.
Okay.
Thank you.
Okay. Sorry about that. Yeah. So what I'm talking about, automobile shipping problem arises for various contexts, like distributing automobiles to the dealer locations. Automobiles are shipped to developing countries. Also, people order cars online and want to get delivery to their home. When people migrate, they want to get their car shipped to the new place. So in all those contexts, we use automobile shipping. Yeah. So what is an auto carrier? So an auto carrier is used to transport automobiles to various locations. So it structure. If we look at the structure, we can see there is a tractor in front, and there's a trailer that has a platform. And on the platform, there are several automobiles are loaded. So if we want to access one of the automobiles in between, in the middle, we want to have a clear path to the exit. So the exit is always used to load or unload an automobile to the auto carrier. So in that case, reloading happens when one automobile is unloaded and loaded back to the auto carrier for facilitating to unload another automobile. So reloading is a time-consuming, costly, and risky operation. So in different automobile shipping problems, we try to minimize the reloading operations. So several studies have conducted analysis on automobile shipping problem, where they considered allowing reloading operations, but some other studies excluded such possibility. So the research gap is that no study have explored the impact of auto carrier loading policy on the trade-off between solution quality and computational complexity. So this study aims to fill this research gap. So in this study, we considered two types of reloading policy, that is policy 0, where reloading is not allowed, and policy 1, where reloading is allowed. So there are several optimization decision problem in automobile shipping analysis. Those are partitioning, routing, loading, and reloading. So what is partitioning? Partitioning is how are automobiles grouped and assigned to different auto carriers. Routing is determining what will be the order of visiting, pickup, and drop-off locations. Here, loading decisions are like which automobile will be assigned to which slot. And finally, reloading decisions are like whether reloading should be allowed or not. So for a given set of automobiles and a given set of auto carriers with loading constants, the focus of my dissertation is to optimize all those decisions, like loading decisions, reloading decisions, routing decisions. So in this study, we focus on the loading decisions only and various related reloading policies. So what is a state of an auto carrier? So if we have some automobiles and their corresponding IDs, and we want to assign those automobiles to an auto carrier, a state indicates which automobile is assigned to which slot by their ID. So in this case, we can see an array that is 312. 312, that indicates the automobile 3, 1, and 2 are assigned to first, second, and third slot of an auto carrier. So what is the loading constraints? The loading constraints are some restrictions that prohibit certain assignment of automobiles to auto carrier slots. There are two types of loading constraints. Those are single car constraint and pairwise constraint. Here we have two scenarios. In the first one, we do not have any loading constraint. In the second one, we have some loading constraints. We can see there is a route that we should follow for this for this case, we have automobile 1, 2, 3 to be delivered to dealer location 1, 2, and 3. So if there is no loading constraint, we can assign automobiles to any order, which is the best. We can we can assign those automobiles in this way and deliver 1, 2, and 3 to the corresponding dealer locations without any difficulty. But if we have some loading constraints, like the exit slot cannot hold automobile 1 and 2, and we need to follow the same route, in that case, some problem arises. Like if we want to deliver, so in this case, we cannot freely assign automobiles to the auto carrier. We need to maintain that constraint. So in that case, 3 is assigned in the first slot and 1 and 2 in the second and third slot. So when we reach dealer location 1, we want to deliver 1, but 3 is in front of it. So that's why we need to unload and reload 3 to deliver automobile 1. In that case, one reloading operation happens. So similarly, we can see here, we have another reloading operation. So we solve this problem by building a space state network. The idea of space state network is described here. So from the previous case, we can see we have initially 3, 1, 2. So in the space state network, we actually built a multi-stage graph where each stage is corresponds to the visiting locations of the auto carrier. So initially at location 0, we can see 3, 1, 2 is assigned to the automobile. But in how many ways we can assign those automobiles? We have 2 ways. So those are the 2 ways assigned to this location and this stage. And at dealer location 1, we can see we have only 2 of them, 3 and 2. In how many ways we can assign those automobiles here? So those stages indicate in how many ways we can have the state of an auto carrier, and the link between those states indicates what's the cost of transitioning from one state to another in terms of number of reloads. So how we find the feasible states in one stage? So in that case, we consider all loading constraints such as single car constraint and pairwise constraint, and use a procedure that is called loading state generation procedure that gives us all feasible state that is possible for a given set of automobile and a given set of auto carrier slots with different constraints. So now how we calculate the cost of the link? So in this case, I have a procedure here, but I'm not going to go in details. So we compare between 2 states and try a 3-step procedure to calculate the minimum number of reload necessary to transition from one state to another. So finally, we have the policy 1, in which rerouting is allowed. In this case, we have a route. The numbers indicate the automobile IDs, and the sign indicates whether it's a pickup or drop off. So here, this is a multi-stage graph. So each stage corresponds to each visiting location of the route. So each node represents the feasible ways or state that's possible with the set of automobiles that is now on the auto carrier. So in that case, we can see we generate all those feasible states by brute force. So we can have all possible states when a few automobile IDs are there. So and the connection made between 2 states, we do not, I mean, we try to connect all states between 2 stages in this case for policy 1. Yeah. For policy 0, we do not have any reloading operation. So in this case, auto carrier works like a stack of automobiles. In that case, we try to fill the auto carrier in the same order of visiting different locations in the auto carrier route, and we try to see whether we can load and unload those automobiles to the auto carrier without any reloading operation. So By this, we just try to see if there is a feasible way of loading or unloading all automobiles here. Then we have three variants of policy 1. Policy 1A, 1B, and 1C. Policy 1A is already I have described previously, but we introduced two new policies, 1B and 1C. In all of them, reloading is allowed. So how policy 1B and 1C different from the policy 1A? So in policy 1A, we used to use a brute force method to generate all the feasible states. But here we generate new states, which we called induced states, with some restriction from previous states we have, instead of trying all possible states. So for state generation, here I visually describe how we generate the state. So here, when we load one automobile, we try to place in empty slots. For reloaded automobiles, we do not change their position in this case. And when unloading one automobile, the reloaded automobile can be reshuffled and assigned to any slot in this case. But for policy 1C, we see for both loading and unloading, the reloading of automobiles do not change their position. That means when an automobile is reloaded back to auto carrier, it should be placed in the same place it was before. And for connecting between two stages, for policy 1B, it's same as policy 1A. That is, we connect all states between two stages. But for policy 1C, we only connect the induced states. That means there is less number of links here. Then for experiment, we take Florida state, different metropolitan areas of Florida state, where the depot is located near Orlando. And the distance between those locations are calculated using Google Maps distance metrics API. For auto carrier, we have selected one 6-slot, 2-level auto carrier. There are 3 types of automobile, type 1, 2, and 3, based on different size like small, medium, and large. We have considered all standard loading constraints. That includes single car constraint and pairwise constraint. For reloading cost coefficient, we assumed 50 miles per reload. Number of routes per experiment, we have 250, and number of random experiments we did is 100. So how we did the experiment? So in this case, for each experiment, we try to generate 250 random routes. For each route, we try to calculate the loading and routing total loading and routing cost. So the route with the minimum cost is selected as the best route or best result from one experiment, and that gives us one solution time and cost for each of the experiments. Then we try to plot the results, the solution time and cost for 100 experiments for policy 1, policy 0 and policy 1A. We can look at the figure. The green dots indicates the results from policy 1A and black dots indicates policy 0. So we can see that for policy 0, the solution time is very small because we just try to check whether it's feasible to load and unload automobiles like a stack. But for policy 1A, we try to build and solve one network and try to find the shortest path from first state to last state. It takes almost on average 100 seconds for each experiment. For cost, we see in 52% of the cases, policy 1A yields lower cost than policy 0. On average, cost saving for policy 1A is 88 months. Now we introduce policy 1B between policy 0 and policy 1A. In that case, we can see solution time is significantly decreased, which is 23% of policy 1A of solution time. But for for the cost, we can see for all the 100 experiments, policy 1B also is the same cost as policy 1A. Although all those experiments yielded the same result for policy 1B as policy 1A, but policy 1B can yield suboptimal solution because policy 1B do not include all possibilities of states like policy 1A. This is one example where I show that for the same route, policy 1A, how the space state network looks like in policy 1A and policy 1B. We can see for policy 1Bs, we try to map those exactly same as policy 1A. And we see there are some missing states here for which the solution for policy 1B can be suboptimal. Now we introduce policy 1C between policy 0 and policy 1A. So we can see policy, we see more improvement in solution time for policy 1C. It's almost close to 0. But we can see policy 1C here. Policy 1C is smaller cost than policy 0, obviously, for the 50% of the experiments. But policy 1C yields the same total cost as policy 1A for 89% of the experiments. That means for 89% of them, 89 of them has the same solution as policy 1A. But the solution quality is just slightly decreased, where we can get greater improvement in solution time. For full-scale analysis, to analyze like a real data, we select a few states here. So randomly, we randomly generated the shipment orders proportional to the population of the metropolitan area. We consider 5 states and their major metropolitan cities. Number of auto carriers here 10. Number of automobiles to be shipped is 45. We used 5 single level and 5 two-level auto carriers. 800 sets of route per auto carrier type is used, and in total 80,000 auto carrier routes are there. So solutions are generated under policy 0, 1B, and 1C. So next, this is
last 3 minutes, Sajeeb. Last 3 minutes.
Yeah, I'm almost done. Okay, thanks. We use this analysis framework to solve this full-scale problem. We try to minimize the sum of auto routing and loading cost when automobiles are given, a set of auto carriers are given, and also a set of pre-generated routes are given. So from the result, we can see that we show the trade-off of total cost and computation time for the full-scale analysis. Here we see the similar result as benchmark problem result. We see that policy 1B and 1C takes more time, but reduces the cost significantly. Policy 1C costs 100 more than policy 1B here, just a slight increase in cost. But we can see policy 1C yields comparable solution with significantly less time here. So in conclusion, we can say we developed a space state network-based solution approach for auto carrier loading and unloading optimization. We have quantitatively explored the impact of auto carrier loading policies by analyzing trade-off between the solution time and solution quality. Two proposed loading policies, namely policy 1B and policy 1C, can yield a desirable compromise between solution time and cost. Policy 1B requires less than 25 of the solution time than a brute force algorithm, and policy 1C requires even less time, although the disadvantage is it can generate suboptimal solutions for some cases. Thank you so much for listening to my presentation. If you have any question, please feel free to ask.
Thank you, Sajeeb, for your presentation. Anybody has questions from the audience? Please, you can unmute yourself and ask the question. I just have one question for you. What is the so you have these results now. What is the practical implication of this? Like what can analyses like this bring about in terms of the state of the world?
Yeah, so you can see I have used 3 policies here. Policy 0, policy mostly 4 policies. Policy 1 has 3 variants, so 4 policies here. Policy 0, policy 1A, 1B, and 1C. So policy 0 focuses on no reloading operations. On the other hand, other policies like focuses on reloading operations, but different policies here have a different extent of having reloading operations. Like in policy 1C, reloading operation is not that optimized. In policy 1A, reloading operation is totally optimized. So in this case, we can see we also have different solution time for different policies. As we try to optimize more the reloading operations, it takes more time for solution. So in this case, policymakers or transport agencies can select which policy they should select based on their needs. If the reloading cost is very high, they can select more the solution approach that focuses more on the optimization of reloading operations. So this can be the applications.
Great. Thank you so much, Sajeeb.
Yeah.
Anybody else has any questions? All right. The next presentation that we have is within-day dynamic traffic equilibrium with heterogeneous information, considering strategic forecasting of travel time. Authors are Xiaoyu Ma and Xiaozheng He. Presenter is Xiaoyu Ma. Xiaoyu Ma is a PhD student in the Department of Civil and Environmental Engineering at Rensselaer Polytechnic Institute, pursuing a degree in transportation engineering. Her research interests include transportation modeling, operation, optimization, and control for emerging transportation systems. Over to you, Xiao.
Thank you for your introduction. Let me share my screen. Okay, can you see my screen?
Yeah, we can see your screen.
Okay, thank you. Hello, everyone. I'm Xiaoyu Ma. I'm a PhD student in transportation engineering at RPI. Today, I will present my research work related to the within-day dynamic traffic equilibrium, considering heterogeneous information, including strategic forecast information. This is a joint work with my advisor, Dr. Shan He. First, a little background. Nowadays, we can receive many types of traffic information, such as travel times, accident information, road condition, etc., through many types of channels, for example, navigation apps, message signs, radio or telephone services. The provided information in practice usually reflects the instantaneous traffic condition. For example, the real-time travel time at the current circumstances. So to further illustrate, here I create a small example for demonstration. Now we assume we provide instantaneous travel time information to the travelers, and the travelers make route decisions. We have 2 routes. At the current circumstances, the travel times are 3 minutes and 5 minutes respectively. Then we can have more travelers choosing the route 1 because it's the route 1 has lower travel time, and we have less travelers choosing route 2. But we may end up with 5 minutes and 4 minutes for the 2 routes respectively. So actually, in the end, we have more travelers are using the path with longer travel time. So this phenomenon is called information overreaction. And in this case, we can calculate the total travel time is 34 minutes. But if we consider we provide some kind of forecast travel time information, it's like we can predict that more travelers will choose to use route 1, so that the travel time will increase to be like 5 minutes. And similarly, the travel time of route 2 will be decreasing to 4 minutes, for example. So if we provide such forecast travel time information, then there will be slightly more travelers choosing route 2. then we may end up with 3 minutes and 5 minutes at the end as the actual realized travel time for the two routes. So in this case, we can calculate the total travel time. It's 29 minutes, which is smaller than the previous case. So this indicating that forecast travel time information may help reduce congestion. So this leads to the question, can we leverage advanced forecast information to improve the traffic system performance? This actually motivates our research, like a first step to understand the impacts of information on travelers' behaviors and traffic systems, considering the forecast of information. Okay, so in the literature, the studies related to the impacts of traffic information on traffic systems can be divided into these three categories. Actually, our research is in the third category, which is within the traffic dynamics. And in the literature, the relevant studies are mostly based on simulations. Theoretical model is very limited. So this paper intends to theoretically model the within-day dynamic traffic equilibrium with heterogeneous information, considering strategic forecasting of travel time. So the basic idea is that we assume there are two types of information provided to two groups of travelers in the system. The first type is instantaneous travel time information provided by a regular information provider. And in this work, it is obtained from a dynamic network loading model, but in practice, it can be obtained by collected data, for example, sensor data, GPS data, etc. And then another group of travelers receive forecast travel time information. It's provided by a strategic information provider, and it's obtained based on strategic thinking. It's a concept in economic theory, which assumes that players make decisions based on analysis of what others might do. So essentially, the forecast information is obtained by based on some forecast traffic dynamics, which is assuming that all travelers will choose to follow the other type of information, that is the instantaneous travel time information. And based on that, we can have some forecast on the traffic dynamics, then we obtain the forecast information, just like the logic I show in a small example in the very beginning of this presentation. And in addition, simultaneous path and departure time choice is considered in this research. Okay, so here's the modeling framework. From the very top of the figure, we can see the two types of traffic information. Given that this information, travelers can perceive some level of disutility, including travel time, arrival penalty, and the perception error based on random utility theory. And then given that disutility, travelers make decisions. Here we use the discrete choice model to model the traveler's decisions. Then we can get the realized path departures, which determines the actual traffic condition on the road, and then which in turn determines the traffic information provided to travelers. So actually at the equilibrium, there falls a loop, and in a sense it's a dynamic loop because the traffic information is dynamically updated at each time interval. And also travelers' disutilities and the decisions are also updated at each time interval until they actually depart. Okay, so, So we call this dynamic equilibrium is dynamic stochastic user equilibrium with dynamic heterogeneous information. A typical equilibrium condition is that no one can further reduce their perceived disutility by unilaterally changing their choice decisions at each time interval. Here is the definition of the equilibrium. I will not go into the details due to time limit. The equilibrium can be formulated as a fixed point problem and solved by method of successive averages. We do have some propositions and theoretically proved them in this research, but again, due to time limit, I will not go into details. And some results can be reflected in the numerical examples. Okay, So let's move on to the numerical part. The numerical example is conducted on an Helm network. In the experiments, we have sensitivity analysis on two parameters. The first one is the dispersion parameter in the logic-based discrete transfer model, which represents the sensitivity of travelers to the travel cost or disutility. And then the other parameter is the proportion of travelers receiving forecast information. Okay, at the base case, we set the parameter theta equals to 1, and the proportion of strategic class travelers is 50%. Here, this figure shows the results on the past departures of the two classes of travelers for an selected OD pair. So we can see that at the right figure, the peak for the strategic class is actually more distributed than the other one. This means that the forecast information can predict some congestion in the future, so that some travelers choose to depart earlier. And then this may imply that the forecast information can help to distribute the traffic demand and to reduce congestion. Here shows the analysis about information accuracy, which is measured by the difference between the provided information and the realized travel time. So of course, the lower the difference, the higher the information accuracy. So from the figure, we can see that the forecast information is more accurate than the other one because the relative difference is in a smaller range. From about -4 to +2. Okay, so then here is the information accuracy for all the OD pairs. We can see the results varied by the two parameters. Okay, overall, the strategic class gains benefits in information accuracy. So from the first one, from the left figure, we can see that as more travelers are sensitive to the travel cost or disutility, the relative difference is increasing. That means the information accuracy is decreasing. So, and such decrease is more severe for the regular class. And then at the right figure, we can see as more travelers choose forecast information, the similar trend presents, but the gap between the two classes are only slightly increases. Here shows the results for the average systematic disutility. From the figure, we can see that the average disutility both increases for the two classes as more travelers receive forecast information, and the regular class travelers who switch to strategic class would feel more satisfied than before because they will have lower disutility. But their experience is not as better as expected because as more travelers receive forecast information, we can see the disutility is actually increasing. So then here shows the results on the total system travel time. We can see the increasing trend indicating that as more travelers choose to receive forecast information, then the total travel time is increasing. Here the dashed line is the traditional single class DSUV case, which is the dynamic stochastic user equilibrium, which assumes that travelers are receiving perfect information. So from the result, we can see if the proportion of traffic strategic class is smaller than some threshold, for example, here is around 0.5, then providing some imperfect information can help reduce the congestion compared to providing perfect information. Okay, so some conclusions and insights. So in general, travelers receiving forecast information can gain more benefits in terms of reduced disutility and higher information accuracy. And the second is increasing the forecast information transparency may reduce the system performance in terms of the total travel time and worsen travelers' experience in terms of the disutility. And a trade-off on the size of strategic class is needed if we want to earn revenue by providing forecast information with high reliability. And at the same time, we want to enhance system performance, that is to reduce congestion. Some future directions. So first, we can model the class composition of travelers as an endogenous variable. But in the current research, the class composition is just given. And we can also consider information pricing. And finally, we can consider the competition relationship between the different information providers. Okay, then that's it. Thank you. Due to time limit, I only present the results on. I only focus on the numerical part, but if you are interested in the technical details, please email me. I can give you more materials. All right, thank you.
Thank you so much, Xiaoyu, for your presentation. I invite questions from the audience. For those of us who are unaware, what do you mean by information pricing?
Oh, here I mean, because if we want to provide such advanced forecast information, we may like have a pricing on it, because well, from our results, the forecast information can bring benefits to its receivers. For example, the higher information reliability, the lower disloyalty. So in practice, we may have some scheme to decide we disseminate such advanced information to which group of travelers. So in this case, we can implement information pricing.
Understood. Thank you so much, Xiaoyu.
Thank you for your question.
Any other questions to the presenter? Thank you once again.
Thank you.
The next presentation is comparison of travel attitude study methods using online tools. The case of understanding public acceptance of autonomous vehicles. The authors are Chng, Jana Plananska, and Lynette Cheah. Jana is going to be our presenter today. Jana is an expert and independent consultant in the management of electric and smart mobility. She obtained a PhD in business administration at the University of St. Gallen in Switzerland in 2021. Jana has subsequently founded her own consulting company, Jana Plananska Mobility Solutions, advising clients on solutions for electric and smart mobility. During her research and as a consultant, Jana has been focusing on topics related to the sustainable battery value chain, consumer adoption and behavior, digitalization, and automation. As part of her PhD research, Jana also has collaborated with the Singapore University of Technology and Design, namely Professor Lynette Cheah and Dr. Chng, analyzing consumer acceptance of autonomous vehicles. Before her PhD, Jana obtained a double master's degree in international development and political science from Sciences Po Paris and the University of St. Gallen. Welcome, Jana.
Thanks a lot, Nikhil, for a very nice and very kind presentation. So I have nothing more to say but share my screen and start presenting. So yes, I believe that you can see my screen. So yeah, thanks a lot. Yeah, very good. Brilliant. So thanks. My name is Jana, as introduced by Nikhil, and I'll be presenting the results of our research that we have conducted with Chng and Lynette Cheah from the Singapore University of Technology and Design, when we were comparing the different travel attitude study methods, especially the ones using online tools, analyzing the case study of public acceptance of autonomous vehicles. So where did we come from? So traditionally, research of travel attitudes is using mainly the research methods, the self-reported research methods such as surveys as the quantitative research methods and focus group as a representative of qualitative research methods. However, the advent of online environment and mobile phones is allowing us to use a broad plurality of novel research methods or adapt the existing ones to enrich our insights and our research possibilities. However, these novel research methods have not been very widely used to date, and especially not in the context of travel behavior. And therefore, we have decided to actually compare and contrast the traditional and more novel research methods that have been enabled by online tools to also compare their effectiveness, to see their merits, potential limitations, and basically see their application within research. And therefore, we have decided to compare and contrast always two, one traditional and one novel quantitative research method, and one traditional and novel qualitative research method, as you can see in this table. And I'll go into detail in a bit. And the case study that we have decided to analyze is to investigate public acceptance of autonomous vehicles if used for public transit in Singapore. Because vehicle automation is growing, it is one of the 4 revolutions of transport that have been very widely talked about, and the future and will be becoming even more relevant in the future, with a lot of trials already implemented in practice. And Singapore is one of those. However, and so in order for the success of the implementation of autonomous vehicles in public transit is, of course, public acceptance in order for the public to hop on the autonomous bus. However, the understanding of public acceptance of autonomous vehicles for public transit has been lacking, especially across different contexts out of Western Europe and Northern America. And if it has been investigated, it has been using mainly the traditional research methods, such as the quantitative survey that I have talked about. And therefore, we need to basically understand AV public acceptance better using novel research methodologies that would provide us more complete insights. And that is why we have approached this topic using the 4 research methods that I have talked about. And we have decided to develop a questionnaire that was basically the one questionnaire that was adapted then for each of the 4 research methods employed. The questionnaire consisted of an introduction, where we first asked our respondents if they are familiar with what autonomous vehicles are. We have then provided them a definition and informed them also about the current trials that are happening in Singapore. And then the core of the questionnaire came with 5 main questions, where we were asking the respondents to give us words that are related to autonomous vehicles, if they would be willing to use AV in practice. There were 5 questions related to safety of autonomous vehicles, if people consider that autonomous vehicles would increase the safety, would increase the number of travel accidents, etc. Then emotions towards AVs, and finally, we asked our respondents to summarize their thoughts about AVs in a Twitter-length statement. And the 4 research methods that we have implemented, finally, I will go into detail about them. So we have implemented for quantitative research methods survey, the traditional one, and then mobile chatbot survey interaction that was similar, as you can see on the screenshot, was basically raising the same questions as in the survey. However, instead of coming automatically, they were raised by a chatbot that we have previously programmed. We have called this chatbot Alice, and the chatbot was raising these questions one by one. On the platform, we have chosen Telegram, and it was asking the questions in a more colloquial format, because the previous research has shown that if the chatbot is more colloquial, then the trust of the respondents is higher, and therefore also the research insights can be richer. As for the qualitative research methods, we have applied focus group that was run on Zoom like the platform that we are currently on. And then we have also used a mobile chat group, also Telegram, where basically we have pre-programmed the questions that were coming to respondents within 3 different groups in the time windows of 2 to 3 hours, and respondents within those time frames were supposed to answer these questions. And we have conducted the research in Singapore. We have made an open call for participants on online platforms. In total of 320 participants participated, and the whole study was conducted in English. As you can see here, the participants were split approximately around 100 per the 3 research methods. Only in the focus group there were less participants because, of course, the groups cannot be too big in order to support higher interactivity. And the research was conducted mainly in April 2021, with the chatbot running a bit longer, and the reason why will come right in a second. I'll jump into the results. So we have divided our results into 3 sections: the administration of the method, participant behavior, and the findings related to the case study. So first, in terms of the administration of the method, the recruitment was harder for novel research methods for the chatbot interaction and mobile chat group discussion. We assume because of the limited familiarity, because people had to have the app, the Telegram app, downloaded for both of them, and therefore we have also introduced the financial reward in order to facilitate the recruitment. That really worked, however, also increased the costs of the study, which was then much higher for the qualitative research methods, in which every participant received a financial reward because of the time commitment, and lower for the quantitative research methods. The running costs were very low for us because we have conducted the research within university settings where the software licenses were for free. However, if not, then of course this license for Zoom or for Qualtrics, of course, would have substantially increased the costs of the study. The effort of the researcher has been shown to be consistent with the traditional research methods, and therefore for the quantitative research methods, basically the administration as well as data analysis were very straightforward, because once programmed, we didn't have to monitor the survey over time to time in order to see the number of participants, and the analysis was also very straightforward using quantitative research methods. And the qualitative, on the contrary, the qualitative research methods, the engagement had to be higher because we as researchers were actively moderating the focus group, and also had to regularly monitor the chat group, and also tried to increase the interaction. And as for the data analysis, of course, transcribing the insights from the focus group and then coding the text, of course, was much more time consuming and demanding than the data analysis from quantitative research methods. As for the participant behavior, firstly, participants did not shown any or reported any difficulties when conducted the research. There was a final question open-ended where people could have raised their concerns, however, none were raised. So it shows us that currently people are very well aware and familiar with the online study methods, and however, the biggest problem was interactivity, which was very low, especially within the mobile chat group, where we have seen a lot of inactive participants or a lot of echoing of respondents across each other. And this was much lower in the focus group, where basically us as moderators could have mitigated this echoing and were able to engage more active participation. And finally, we also assume that some participants had concerns with their privacy, because almost 29% of participants of the focus group did not switch on their camera. And in that regard, the mobile chat group could have alleviated some of these privacy concerns because they could have changed their name on the app and did not have to choose a picture as their icon. They could have chosen any picture they wanted to. These findings, we have recapped them in the table that I have copied here for your information. However, it is also featured in our paper that is currently under review in the Transport Research Interdisciplinary Perspective Journal, and that should help researchers to kind of that is recapping basically the main insights that we have gained across these 4 research methods and their administration to potentially help with future research applying this combination of research methods. And finally, insights in terms of the case study. So we have overall seen that there is a cautious excitement and anticipation of autonomous vehicles. So the Singaporean citizens see autonomous vehicles as a technology to come, as a future of transport, so they see it very positively. However, there are still concerns, especially in terms of safety and future implementation of the technology in practice. Some are also concerned in terms of ethics and potential legal issues. And which is also consistent with the literature findings to date. What we also see, and what is very important for us, is to see that the research methods, the findings are consistent, as you can see in the screenshots here, where there are some of the questions compared the results from the survey and the chatbot survey. So we see that, for example, people would be willing to use AVs, and in almost 62% of the respondents of the chatbot, and almost 60% of the online survey. So people are willing to use AVs. This supports the idea that they are supportive of autonomous vehicles and that the results are consistent among the methods. However, the security concerns are illustrated on the graph D, where we see that basically more than 83% of respondents of the chatbot are concerned about potential cybersecurity risks. This number is lower in the online survey, only 73%, but basically comparable with the findings from the chatbot. So the results are consistent, and similarly to the traditional research methods, while the quantitative research methods give us a good basis of insights on the topic, the qualitative research gives us deeper insights and explanation, and a very, very good complements the insights of the quantitative research methods. The biggest limitations that we have encountered, I have already hinted on them, was firstly the small sample size, because it was quite hard to record, especially for the novel research methods, that also led to a non-representative sample of Singaporean population. There was at the end skewed towards younger and male participant, which could have been also attributed to the fact that we have posted the call on university networks, and therefore more university students participated in the research. And therefore, we would encourage further future research to try to broaden the participation and increase the sample size in order to make a generally representative data. And second biggest problem was the limited interactivity of participants, especially in the mobile chat group discussion. And we would also encourage further research to try to identify the factors that would be helpful to increase the interactivity on this particular platform. And therefore, to conclude, these novel research methods, such as chatbot or mobile messaging app, are deliver very consistent data with the traditional methods and the very high quality, and therefore they are a very good example of methods that could be used to enrich our insights. So we very much encourage further future researchers to be using them because they are also very scalable, very accessible for both researchers and the participants, and they are their cost is very low, especially within institutional settings. So we would encourage their further use. For that, we also encourage researchers to consult the table that we have generated to basically have a good start of their basics. However, there are still challenges, especially in terms of the recruitment and limited interactivity. And therefore, we would encourage further research to try to broaden the participation, also, for example, by using different types of question types on these platforms, such as audio messaging or emoticons. And finally, in terms of the case study insights, so as I have said, there is cautious excitement of autonomous vehicles with Singaporean respondents having mainly concerns in terms of safety and technology. And to overcome these remaining concerns, we would encourage Singaporean policymakers to increase familiarity by sharing more information with residents of Singapore, especially in terms of technology, safety, and legal aspects, because people are very much interested in learning more. And finally, also to provide trials and test drives where people could experience autonomous vehicles on their own. And so with that, I would like to thank you for your attention. And also, if any one of you was interested to try the chatbot survey, I have attached here a link to the chatbot discussion, to our Alice chatbot, where we have programmed for the study that is still active. And you can try just for fun if you have never interacted with chatbot or you want to interact with the chatbot about autonomous vehicles. And so with that, I would like to thank you.
Thank you so much, Jana, for that presentation. I would like to now open the floor for any questions. One of the questions that I had with respect to your very interesting study is, I'm actually interested in looking at the sample sizes and the demographics of people who responded to the specific modes. Did you notice any kind of trends towards, you said there was a skew for younger participants, and that is predictable from a university setting, but did you find anything else that was interesting between the four methods on participant demographics or any other interesting things to share here?
Yeah, yes. So it will be also the deeper detail of the demographics profile will be in the paper. I didn't copy it here, but basically what was interesting was firstly that the younger males were tending more to go into the novel research methodologies, and especially to the chatbot survey. So there were also kind of the more, let's say, technologically driven participants would be going to the novel research methodologies, because then basically, because the people who had concerns, especially in terms of time requirements for respective methods, would rather than choose the traditional ones. So kind of the ones who were unsure would jump to the traditional ones, whereas younger male who were more, we assume, likely to know these, especially Telegram messaging app, were rather choosing the chatbot survey. And therefore in the messaging app and the focus group especially, there was more there was a higher share of women participating. So there were these kind of individual differences which we mainly assign to the privacy in technology.
Thank you so much. Any other questions for Jana? Thank you once again, and let's move on to our next presentation. Our next presentation is Decision Field Theory, an Extension for Real-World Settings. The authors are Thomas Hancock, Stephane Hess, Choudhury, and Panagiotis Tsoleridis. Thomas is going to present today. Thomas, I'd like you to start with a brief bio and then can move on to your presentation.
Thank you. Just share my screen. There we go. Can you see the slides?
Yeah.
Okay. Thank you very much. Thank you for attending today. My name is Thomas Hancock, and this is work I've done with Stephane Hess, Choudhury and Panagiotis Tsoleridis. And today I'm going to be talking about decision field theory and extension for real-world settings. And so just an outline of what this presentation is going to be about. Basically, decision field theory is a choice model with psychological rather than econometric foundations. It was developed in experimental psychology by people who often call themselves mathematical psychologists. And they're much more interested in how we make decisions and can we sort of mathematically represent this decision-making process rather than the actual choices themselves, not actually focused on what those outputs actually are. We've previously demonstrated that this model can be adapted for stated preference settings for travel behavior modeling. And we've got a couple of papers on that now. We've shown that we can effectively implement, well, the question is, can we effectively implement DFT also on revealed preference data? So there's going to be a few additional steps. And this is really because this model was born and created for laboratory settings in experimental psychology. So it's quite a long way from the real world. And so these models, what do they actually look like? They often have perception and process parameters. Basically, because they're trying to capture something about the choice deliberation process. So they're trying to conceptually sort of recreate the decision-making process. And this means they often can do things like also predicting choice response time. So they're not just focusing on predicting choice outcomes. There's many different variants, almost as many models as papers. So whereas we might often use sort of standard models, multinomial logic, for example, and have different specifications for the utility, mathematical psychologists often have different specifications in terms of how the model actually works. So it took us a while to kind of sift through all of these different models and work out which one was actually going to be best to be brought across into sort of real world modeling, but that could also try and capture some of this actual decision-making process. So we particularly focused on accumulation, or also known as sequential sampling models, and particularly decision field theory, which I'll be talking about today. Decision field theory attempts to capture the stochastic nature of deliberation, and its previous focus has been on explaining specific contextual effects that have been found within the field of behavioral economics. So what does decision field theory actually look like? This is part of an example simulated decision-making process under a DFT model. So what we have here is we have 4 different travel modes and attributes describing those modes. And this is actually 4 different modes that I could use for my commute into Leeds University. So we've got different travel times, rate of delays, rate of crowding, and cost here are the 4 attributes. Now, I might have an initial preference based on my previous experience. So in this case, my initial preference is for local train. And it might be that I've used that most often. I then look at the time and think, actually, the national train that has fewer stops on the way to Leeds is going to be faster. Therefore, I'm going to choose that. So my preference for national train increases. My preference for the other modes decreases. I then consider other attributes over time. So for example, rate of delays, and then my preference for the trains goes up, and I might consider cost, crowding, etc. Until at some point, I have to make a decision. So there's 2 different ways that our DFT model can come to a stop. You can either have some sort of preference thresholds. So for example, the first alternative to reach a preference value of 3 would mean that local train has been chosen. Or you could have a time threshold. So at some point I need to just get on some roads and get to work. I can't just deliver it all day. There is some point when I'm going to have to make that decision. So it might be that I'm not entirely satisfied with my choice, but I have to just go and make some journey. So why might these models work well for travel behavior modeling? So this really comes down to the question, does a better representation of the choice process lead to a better representation of the outcome? So these models, I've talked a bit about some of their previous benefits in terms of explaining contextual effects, also capturing choice response time. Crucially, the perception and process parameters allow for more intuitive methods for how to include additional data, such as eye tracking data. And they may also better capture softer factors such as emotion and stress. Our initial findings for SP data suggest DFT outperforms random utility models in terms of model fits. There are negatives as well. These negatives include the fact that these models can be more computationally intensive, and we cannot yet equivalently obtain willingness to pay measures. And that's something we're working on. And this is due to the stochastic nature of the decision-making process within the model. So you could have a way of finding a substitution effect where you increase one attribute level in exchange for another, but then in another simulation, you don't look at the same attributes the same number of times and the preference changes. So that wouldn't work. For most data sets in travel behavior modeling, especially for review preference, we simply do not observe the choice deliberation process. So it's quite hard to imagine what's actually happening there. We don't really see what's happening. Now, DFT is, however, equivalent to random utility maximization models in that you have some number of inputs and return choice probabilities. So I can use them in that equivalent sense. So I could use simulation and simulate preferences like this, but it's simpler and easier to use expectation and covariance of the preference vector. So I can use way of calculating the probabilities much more simply using that. So if we're going to step out of the laboratory, there's going to be more real world variance. So the example I like to talk about here is about a year or so ago when my son was learning to walk. He was doing really well, walking around perfectly well indoors. We went out to the local park and he started falling flat on his face. And what was happening there was simply that there's more variance in the real world. The grass is slippy, there's slopey paths. There is more noise all around him. There's more distractions. He's wearing shoes now. He was just in his bare feet before. So there's all this additional noise in the real world. There's all these extra factors that you have to take account of. And travel behavior modeling is no different. There's a lot more variance in the real world. So how are we going to capture that additional variance? So in a standard DFT model, there is an error term which is added to the preference vector at each preference updating step. And that is assumed to be from normal distributions with the same variance for each of the preference values. So basically, the variation for the different modes in my example there is going to be the same. However, in a heteroscedastic DFT model, what we have is variances of different sizes. So what we're saying here is that the amount of noise in the process is going to be different. So what that would look like in this graph here would be that we'd have some where there's larger jumps in terms of, because you're taking draws from a normal distribution with a larger variance. So you'd get some alternatives that jump about a bit more. So you're basically trying to capture that additional variance. So to our two case studies. The first is we used the London passenger mode choice dataset, and many thanks to Tim Hillel and colleagues for making this publicly available. So 4 modes, walk, cycle, transit, and drive. A lot of data augmentation to generate attribute levels. Again, thanks to Tim and colleagues for doing that. And then there's more than 50,000 trip observations. So an example path here of someone going between 2 different points across London. And in this case, depending on which mode they take, the route's actually going to be very different as well. So In terms of what this model specification looks like, within the DFT model, we have what we call the attribute matrix. So this is where we plug in all of the relevant attributes describing the alternatives. We're going to use just very standard attributes here. Travel time for walking, travel time for cycling, travel time for transit, and for driving as well. We've got out of vehicle travel time and in vehicle travel time. We have cost, and then we have socio-demographic factors going into this column here. So for example, for cycling, it's based on whether someone, it's based on the gender, age, and weather at the time of year. So in winter, people are going to be less likely to choose the cycle. For additional parameters for the DFT model, which are these sort of psychological parameters, which represent the decision-making process. One is the estimate for the number of preference updating steps, because we don't know the decision time in this case, so we just had to create an estimate for that. If we had response time, we can think about ways of linking this number of preference updating steps to the response time. For our base models, what we see is good improvements for the DFT model over the MNL model. And despite the extra parameters, the adjusted rho squared and the BIC are better as well, which is good. Still looks better for the whole data sample as well. So DFT doesn't look to be replicating the data. Yeah, so next we have the other models we've included here. So we've tried a number of different random utility models across nested logit. We've got heteroscedastic logit. We've got asymmetric logit models here. This is from Timothy Braithwaite and John Walker's paper on asymmetric logit models. We've used a couple of their models there. And basically going beyond MNL results in models that kind of catch up with DFT. But then if we move to the heteroscedastic DFT model, we see a good improvement again, more than 500 units improvement to that model. And that means that it's now our best performing model. So it's capturing that extra variance there in the data. And we can look at some model outputs, for example, elasticity for car travel time. These look fairly realistic. The DFT model possibly underestimates that value, but our heteroscedastic DFT model doesn't. It's much more in line with the MNN cross-nested logit models. Good. Similar for the relative importance of in-vehicle travel time. So this directly translates as a willingness to pay for MNL. It doesn't quite have that same interpretation under a DFT model, but it's roughly equivalent. So I think maybe like in the average simulation, it would be equivalent. But of course, there's that extra noise in the DFT model. So we need to do more work into understanding how this actually varies. But basically, the relative importance, they're not too different here, which is kind of promising. It suggests it seems to be realistic. Our second data set is from Leeds itself. We've got what we call the decisions data set. This was collected by my colleague Kiara Kalashri for working her PhD. More than 10,000 trips in the UK, most of them in Leeds. In this case, 6 different travel modes: walk, cycle, bus, rail, taxi, and drive. Colleague Panos did amazing work with data augmentation to generate attribute levels. And again, we set aside 10% of the data for out-of-sample validation. And many thanks to RMove, which made this data collection a lot easier. RMove's a really good way of collecting real data. We have an attribute matrix, again, this time travel time, in-vehicle travel times, out-of-vehicle travel times, and costs. And I should have said before, the MNL specifications basically using all the same attributes. So the underlying specifications are really quite similar. It's just the model structures that are different. In this case, similar to before, the DFT model is about 100 units better than the MNL, which is still better once we account for the difference in the number of estimated parameters, which is good. In this case, DFT is actually better than our other competitors. And we do again see an improvement going to the heteroscedastic DFT model. this time slightly less improvement, but it is a smaller, significantly smaller data set, so it's not really surprising. Our elasticities for power travel time are smaller than they are in London. That makes sense. It's cheaper to live in Leeds than it is in London. But they're very similar across the models, which I guess is encouraging, is suggesting that the models are not completely random. They're getting sensible outputs from them. And the relative importance of walking, in this case, looks pretty similar from DFT to the heterogeneous DFT model. Finally, one thing to note is that this development of this heterostochastic DFT model is very much for revealed preference data. What we see here is the improvement for RP datasets and SP datasets, basically absolutely zero for the SP datasets. This model improvement makes no difference at all for state of preference. This is really a method for capturing real world behavior. So what we've done here, I'd say we're helping DFT learn to walk in the real world. And we've got a simple model change to capture heteroscedasticity in the RP mode choice data. And we see significant improvements for the RP data, not for the SP. Our next steps is to try and help DFT to run in the real world. So there's a lot more things to try and work out. So correlation between the variances, for example, might help us move towards a nested DFT model, capturing correlations between the alternatives, underlying correlations. We really want to try and see if we can do something about this lack of willingness to pay measures for DFT. That would be excellent if we can do something about that. More to do in terms of looking at those elasticities and how realistic they are. We also want to do longer term forecasting. So when I say that, I'm talking about we just need to do more forecasting in general. This is a thing within choice modeling. I really like the example earlier in this set of presentations, moving from the morning data to afternoon data. You know, some significant change, and can we see if the model still works? We need to try this for DFT, changing it across a more significant change in context. And with that, I'll just say, please use Apollo. Apollo is great. And my colleagues at Leeds have done great work developing it. I think it's a brilliant tool. I couldn't have done this work without it. And finally, thank you to all of you for staying on to quite a late time in the UK at least. So thank you very much for listening.
Thank you very much, Thomas, for your presentation. We'll open the floor for questions. If you have any questions for Thomas, please unmute yourself and you can ask the question. Okay, so I don't have any questions for you. I would like to wrap up this session by concluding. We had 6 presentations, each looking at different topics, and we also have 6 different topics that we explored. I would like to thank all the presenters for their time and presenters for their effort. Great studies, and we look forward to reading more on these in the coming months. I just have one piece of announcement from Kara, and that is that there is a pet parade that is going to happen starting at 4. The Zoom link is on the chat box. Please feel free to attend and say hi to everyone who's there. If you have a pet, feel free to have a participation. If not, we would like to thank all the presenters once again. My name is Nikhil, and I wish you a great weekend.